Welcome to Chapter 21 of our course MEC410. This week we're going to study AC and DC motors. There'll be a series of multiple choice or numerical answer questions and a Blackboard homework assignment. Because the questions are fairly simple, multiple choice or simple calculations, there's no need to upload an Excel spreadsheet for the Chapter 21 homework. Shown in this slide is the general architecture of an AC induction motor. The rotor revolves within the stator, a fixed electromagnet housed inside a metal frame. A drive shaft supported by bearings is fixed to the rotor, supplying torque and speed to an external mechanism. A cooling fan conducts heat from the stator coil magnets out the rear of the motor. The conduit box holds the electrical wires from line power and distributes them to the windings. The angular speed of the magnetic field rotating around the stator is called synchronous speed, N sub s. To calculate synchronous speed, multiply 120 times the line frequency and then divide by the combined number of north and south stator poles. The table on the right shows the most common synchronous speeds for both 50 Hz and 60 Hz AC line power. Doubling the number of poles will halve the synchronous speed. Except for a special type of AC motor called a synchronous motor, the rotor does not rotate at the synchronous speed. This slide shows the derivation of the synchronous motor speed formula. Referring to the image in the upper left corner, a complete cycle of EMF is generated as a north-south pole pair passes a coil winding. F equals the line frequency, 50 or 60 Hz, which is cycles per second. P equals the number of north-south poles. And N sub s equals the synchronous speed in RPM. N sub s over 60 equals the synchronous speed in revolutions per second. Referring now to the graph in the lower left corner, in the first half of an EMF cycle, the north pole of the rotor passes a coil winding. In the second half of an EMF cycle, the south pole of the rotor passes a coil winding. Then the number of cycles per second equals the revolutions per second times 1 EMF cycle per 2 poles times the number of poles per revolution. Substituting values, F equals N sub s over 60 times a half times P, which equals P N sub s over 120. And then solving for N sub s in a motor application, N sub s equals 120 times F over P. For all AC motors except a synchronous motor, the actual motor speed depends on the motor load, a phenomenon known as slip. You calculate slip as a percentage of the relative angular speed between the rotating magnetic field and the rotor divided by the synchronous speed. Algebraically, slip equals the quantity N sub s minus N sub r divided by N sub s. N sub s equals the synchronous speed, and N sub r equals the rotor speed in RPM. Typical slip in AC motors ranges from 0.5% to 8%. Increasing the load on an AC motor causes it to slow down, thus increasing the slip, the rotor current, and the torque. An AC motor settles at an equilibrium speed when the motor output torque equals the load torque. At that point, the motor provides just enough current output to deliver the required torque. Let's look at a typical torque speed curve for an AC induction motor. Locked rotor torque, otherwise known as starting torque, is the torque output of the motor at a standstill. As the motor accelerates, the torque output reduces until it hits the pull-up torque. Then, as speed continues to increase, the torque increases until it peaks at the breakdown torque, sometimes called the pull-out torque. When the motor speed is at 100% of its rated speed, which is less than the synchronous speed by the slip percentage, it produces a full load torque. Running an AC motor at the synchronous speed would produce little or no torque, which of course defeats the purpose of buying an AC motor in the first place. The slope of the torque speed curve near the full load torque indicates the degree of speed regulation possible. The flatter the slope, the more that speed can be changed without changing torque. The National Electrical Manufacturers Association, NEMA for short, defines three-phase AC motor designs based on the torque speed curves these motors exhibit and other operational characteristics. For example, you would want design D if you needed a very high startup torque, as motors of these type have much higher startup torque ratings than the other motors. Each type of NEMA motor has a specification on current draw. Per the curve in the slide, the highest current draw is at motor startup, dropping as the motor accelerates to steady state speed. Startup current is typically 6x to 9x of operating current. This chart compares all 5 types of NEMA motors for torque, current, slip, and energy efficiency. A few notable conclusions can be drawn from the data. Type D motors have the highest starting torque and are usually used in machines that need it, such as presses, elevators, or lifting equipment. Type E motors have a relatively low starting torque, but also low slip and the highest energy efficiency. They're used in applications which need these requirements, such as fans, compressors, and pumps, which tend to be run 24/7. Type A and B motors have low starting torque, but only medium to high energy efficiency. You might want to use one of these for a pump or compressor which doesn't need to be run 24/7. Type C motors have a reasonably high starting torque, but are more energy efficient than Type D motors. Use Type C motors for conveyors, mixing motors, and reciprocating pumps, which need relatively high torque to start, but which run hours lengthy enough to warrant a medium degree of energy efficiency. Synchronous motors rotate at the synchronous speed, regardless of the load on the motor. In other words, the slip is 0. Large synchronous motors operate under three-phase AC power. They have the same stator design as the basic AC induction motor. However, the rotor design is fundamentally different. The rotor contains electromagnets connected to a separate DC power supply. These magnets are stationary poles that attract to opposite poles of the stator, allowing the rotor to move in sync with the rotating stator magnetic field. Synchronous motors are often found in mills and refineries where large motor powers of 500 to 5,000 horsepower are common. That's 380 to 3,800 kilowatts, with motors of larger diameter than the heights of the people shown in the photo at the right. Small synchronous motors operating under single-phase AC power provide power to servo mechanisms which must run at very high speeds. These motors are commonly found in critical aerospace guidance and navigation systems. In a single-phase AC motor, the AC current in the stator winding produces a fluctuating as opposed to a rotating magnetic field. Per the diagram on the right, the north and south poles alternate their location as the magnetic field repeatedly shifts magnitude and sign. The fluctuating magnetic field is equivalent to two magnetic fields rotating in opposite directions. We need to create a net torque on the rotor of the single-phase AC motor in order to get it to rotate. We can do this by creating a secondary magnetic field with an extra winding known as a starting winding. The magnetic field of the starting winding cancels one of the rotating stator fields and adds to the other. After the rotor has attained operating speed, it will keep rotating even when current to the starting winding is off. In a split-phase motor, the lower values of resistance and inductance in the starting winding puts it out of phase with the main winding. A shift in magnetic flux acts to cancel one main winding rotating field and augment the other, causing the motor to start rotating. Split-phase motors run in the range of a 20th to a third horsepower. They're commonly used for fans, blowers, or AC lawnmowers. Dimensional differences in the starting and stator windings are clearly visible in split-phase motors. We have a video demonstration of a split-phase motor stored in YouTube. The URL is given at the bottom of the slide. A capacitor start motor is a split-phase motor with larger windings and an electrolytic capacitor placed in series with the startup winding. During starting, the current through the starter winding I sub S leads the voltage V, but the current through the main winding I sub M still lags V. This typically results in almost triple the phase angle difference between I sub S and I sub M than occurs in a split-phase motor. You then get a much higher starting torque. When the motor nears full load speed, the centrifugal switch opens, disconnecting both the starting winding and the capacitor from the circuit. The capacitors used in a capacitor start motor are of the electrolytic type. They're usually visible, mounted in a separate box on top or on side of the motor enclosure. Typical capacitance values range from 16 millifarads for a third horsepower motor to 50 millifarads for a 10 horsepower motor. Capacitor start motors are popular in compressors for refrigerators and large pumps where relatively high starting torque is needed. One modest disadvantage is that the big capacitor takes up some space and makes the motor difficult to package in a machine. The permanent split capacitor motor uses a lower value capacitor with a high voltage rating to generate the phase shift between the run and start winding. With no cutoff switch, the starting winding becomes an auxiliary winding at operating speed. The absence of the cutoff switch has one advantage and one disadvantage for the motor. Leaving out the cutoff switch improves motor reliability, as this moving part can be the first component to break in the motor. On the other hand, you need the smaller capacitor to run the motor in safe operating speed, or else your speed will not come close to the synchronous speed. Thus, you do need to accept a low starting torque in this type of motor, roughly 1/4 to 1/3 of that in a capacitor start motor. Hence, designers use permanent split capacitor motors in fans and blowers, where frequent start-stop is needed, and a cutoff switch could fail early in the life of the motor. The capacitor start and run motor has a second capacitor in the circuit, known as a run capacitor, in parallel with the starting capacitor. It combines the benefits of the capacitor start and permanent capacitor motor. Because the start and run capacitors are in parallel when the centrifugal switch is closed, the capacitances add, leading to the highest starting torques found in single-phase AC motors. Once the switch opens, the run capacitor leads to lower operating current and better energy efficiency than found in a capacitor start motor. It will operate closer to the synchronous speed than the other single-phase AC motors. The capacitor start and run motor is used for higher powered applications, such as woodworking equipment or air compressors where high starting torque is needed, but single-phase AC power is still preferred. The disadvantages are clear in the picture shown. The two large capacitors stick out like rabbit ears on top of the motor, making it more difficult to package and wire. In a gear motor, a mechanical gear reduction assembly is attached directly to the output shaft of an AC motor. This assembly greatly increases the torque output of the motor while slowing down the speed by the same percentage the torque is increased. Usually, there are two discrete housings, one for the motor, one for the gear reducer. The gear reduction housing includes gears, shafts, bearings, couplings, and means of lubrication. Spur or helical gears are used where the output shaft is parallel to the input shaft. Bevel or worm gears are used where the output shaft is perpendicular to the input shaft. Customers purchase gear motors where the effort to design and build a custom gear assembly for their high torque application is large compared to the cost of buying a gear motor. This is common when their machine is large and expensive and they only need to buy one gear motor. 1,000-to-1 gear ratios are common in gear motors. This means the torque output of the gear assembly is 1,000 times as large as that of the motor. The speed of the output shaft is only 1,000th of the speed of the motor shaft. Gear motors are popular in large mechanical lifts, medical equipment, and power jacks. They operate on either three-phase or single-phase AC power, depending on the design of the motor itself. A universal motor gets its name from the fact that it can be tailored to operate under both DC and AC power. The basic design is similar to a typical DC motor, and minor modifications are needed to run it on AC power. The field coils are analogous to a stator in an AC induction motor, and the armature is analogous to the rotor. The commutator reverses current in the field coils and armature per the AC line frequency. The direction of torque applied to the armature is independent of voltage polarity, determined only by the commutator and polarity of the field coils. This graph compares the torque speed curve of universal motors against other AC and DC motors. Universal motors operate at much higher speeds than all other motors. If your application demands a speed above 4,000 RPM, you are likely to specify a universal motor. Universal motors have high starting torque. Coupled with the fact that they're lightweight and small, they are the motor of choice in many consumer products. You find them in portable drills, power saws, vacuum cleaners, food processors, and lightweight portable fans. We will demonstrate their use in a desktop fan shortly. Universal motors have some drawbacks that you need to be aware of. The commutator makes the universal motor noisy. One reason why the previously mentioned products make a lot of noise. They also emit a lot of EMI noise, and they can throw off the performance of any nearby electronics design. Some companies use power drills as a quick and dirty way to test the EMI susceptibility of their prototype electronic products. In addition, universal motors are not for continuous use, as evidenced in the type of products they are found in. The commutator brushes wear quickly, and consumers are certainly not interested in getting their hands dirty changing carbon brushes. We made a video demonstration of the teardown of a universal motor used for a portable fan. That video is stored in YouTube with the URL given at the bottom of the slide. Please watch it. People who have traveled around the world know about the basic differences in single-phase voltages. That's what affects their daily lives. Single-phase voltage in North America is generally rated as 120 volts 60 Hz, while the rest of the world uses 220 volts 50 Hz. But it gets trickier for three-phase voltages. In North America, three-phase motors commonly run off either 230 volts or 460 volts at 60 Hz, while motors in Asia and Europe run off 230 volts or 400 volts at 50 Hz. There are several variants that are close, but not exactly equal to these voltage levels. Motor controllers run off single-phase power or 24 VDC if they contain mostly digital circuits. This chart shows the wide tolerances allowed on AC motor ratings. IEC 60034-1 allows tolerances of 10 to 15% on efficiency, 20% on locked rotor, in other words starting current, over 15% for locked rotor torque, and 15% for pull-up torque. This means you can't specify a motor exactly per its rated specs. You need to pick a motor per its worst-case specs, at least for the ones shown. You would think, with the major differences in voltage and frequency specs around the world, that you can never buy an AC motor built to work on one continent and try to use it on another one. But that's not true. You can do this, but you need to carefully read charts such as the one in this slide in order to understand how the specifications will change. Per this slide, motors wound for 50 Hz can be used at 60 Hz, but the power output, torque, and speed will change based on both frequency and voltage. For example, suppose you bought a motor in Europe designed for 380 volts and 50 Hz and had it shipped to North America. If you ran it unmodified in North America at 380 volts and 60 Hz, you would find that the power rating is still 100% of the rated value, but that max torque would be only 85% of its rated value. The starting torque only 70% of its value, and the motor would run faster at 120% of its rated speed. If you ran the motor in North America at 440 volts, 60 Hz, the extra voltage input would increase the power to 115% of its rated spec, while the max torque would be increased to 98% of rating and the starting torque to 95% of rating. The speed would also increase to 120% of its rated speed. A motor wound for 440 volts and 60 Hz, but used at 380 volts 50 Hz, will have its properties changed by the inverse percentages. This example shows a fundamental relation in AC motor speed control. Motor speed is controlled by changing input line frequency. Motor torque and current is controlled by changing the magnitude of input line voltage. There are four commonly used methods of mechanically mounting a motor. The one in this slide is called a foot-mounted motor. It works just like the name sounds. The motor is mounted to a flat surface of a motor frame via a rigid flat surface on the bottom of the motor. You tap 4 holes in the frame, put in 4 screws, one each through the 4 holes in the feet of the motor, and your motor is attached to the machine. In a C-faced mounted motor, the 4 tapped holes are placed in the face of the motor as opposed to the machine. The holes are spaced 90 degrees apart and 45 degrees from the XY axes of the motor face. The size of the motor frame determines the diameter of the bolt circle. The 4 screws butt up against a solid metal plate of the machine that the motor is mounted to. A cushion-based motor is used for machines with very high vibrations, where you are concerned that the vibrations will damage the motor over time. This type of motor has a thick rubber pad that separates the motor housing from the mounting frame. The rubber pad prevents a transmission of the machine vibrations to the motor. A D-flange motor is similar to a C-face motor, but in this case, the face of the motor is milled flat, ready to butt up against a separate flange in the machine. The face of the motor has a defined hole pattern in it for the bolts. Enclosures protect AC motors from particles and liquids, providing convective cooling and guaranteeing electrical safety. NEMA and IEC specify enclosure designs. Global certification agencies such as UL, CSA, and ATEX test enclosures for safety specs. The open drift-proof enclosure in the photo to the right prevents particles and liquids from getting inside to the motor at angles up to 15 degrees from the vertical axis. A totally enclosed, non-ventilated enclosure has no openings in the housing and no provision for cooling except large cast heat fins on the sides. TENV is the acronym given to this type of enclosure. It is not airtight, but dust does not enter in sufficient quantity to interfere with motor rotation. You can use this type of enclosure where the motor is exposed to dirt or dampness. However, it's not suitable for an explosive gas environment. A totally enclosed fan-cooled enclosure, TEFC, has no openings in the housing, but there is a fan mounted to the rear end of the motor shaft. It draws in cool air over the hot motor windings and blows hot air out of the rear of the enclosure. As per a TENV enclosure, use a TEFC enclosure in dirty or damp environments, but not where explosive gas could be present. On the other hand, if your motor is located in an area potentially filled with explosive gas, which is typical for a petrochemical factory, you must specify an explosion-proof motor housing. TEFC-XP is the acronym given to this type of motor enclosure. You can be certain about the need for a TEFC-XP enclosure simply by inquiring about explosion-proof requirements for all the other electrical equipment in the region of the plant where your motor operates. The electrical wiring and circuit board within the enclosure must be specified for intrinsic safety. This means that the boards cannot ignite a specified explosive gas or vapor present inside the enclosure. For circuit boards, this usually puts a restriction on the amount of current flowing on any trace in the board. The enclosure must withstand an explosion of a specified gas or vapor inside it. Test labs literally explode a gas inside the enclosure and watch what happens, safely from afar that is. Some of the technicians in these labs rather enjoy the pyrotechnics on display. These are the guys who spent their childhood playing with matches and fireworks rather than playing video games. If you need a motor that holds up under terribly hot and humid weather, not normally fit for human consumption, you can specify an IEEE 841-2001 severe duty motor. Be aware that this motor is not certified for an explosion-proof environment. A severe duty motor is based off the TEFC enclosure. You can get one for 3-phase or single-phase AC power. You are restricted to output power under 500 horsepower and the input voltage less than 4,000 volts. The main differences with TEFC motors are that the severe duty motor has extra fins, IP65 rating protection for the conduit box, and a more durable epoxy paint on the outside. Severe duty motors are used in petrochemical, chemical, paper, and metals factories. These plants often have a corrosive environment, sometimes from ambient temperature and humidity, and other times from chemical vapors in the plant. A washdown motor withstands direct washing with sanitary cleaning fluids, a common occurrence in food production plants. This type of motor also gives off a minimum number of particles in a clean room, which makes it useful for semiconductor applications. The major design enhancements above a TEFC motor are the stainless steel shaft hardware, conduit box cover, nameplate, and FDA-approved epoxy paint finish. There are even drains on the motor feet for the washing fluid to drain through, just like those in a shower. The Viton seat at the shaft entry to the motor seals the inside of the motor from fluid entry. Washdown motors are used in food processing plants, clean rooms, pharmaceutical and medical products, manufacturing plants. They are required by the FDA and USDA in the United States for manufacturing of medicines and food. Now we'll give you a method you can use to specify an AC motor. You need to define what your process is, what type of machine will use the motor, how you will mount the motor, and what power, torque, and operating speed you need. Then you will rule out possible motors based on the requirements or the fact that they're overspecified. You will evaluate the remaining possibilities and optimize the motor specs based on what you can buy or what small adjustments you can make to your machine to accommodate a motor different than what you specified. To specify an AC motor, you must first define your production process, shown in the left column. This was based on the type of motors we've discussed so far, and in which industries certain motors are commonly used. Each of the processes has typical types of machinery associated with it. Choose one of the types of machinery or type in yours. In the third column from the left, pick one of the 4 methods of attaching a motor. The column for environment goes next. I gave you 7 choices. Document all the relevant ones you know of. For ambient temperature and humidity, make sure to write down the peak temperature and humidity. And if you know the vibration level in G's, write that down too. Write down the available electric power for your machine. There are many variants of 3-phase voltages. Higher powered motors, usually above 20 horsepower, are only sold for use with 3-phase power. Specify both starting and operational torque. Here's an example of using the form to specify an AC motor. Concrete mixers are found everywhere that construction workers need concrete to build a structure. This includes roads, bridges, tunnels, buildings, houses, and factories. In other words, everything. This concrete mixer is relatively small, used for the construction of low-rise residential housing. The motor that the mixer needs is located deep inside the housing of the concrete mixer. The motor face attaches to the internal mixer frame, the motor shaft driving the pinion gear pair. The gear ratio is 10:1. It is used outdoors in all seasons and all weather. The maximum outdoor temperature in summer, where the mixer is used, is 40 degrees C. It is directly exposed to the rain. Fortunately, the motor is housed deep inside the mixer, so it won't likely be exposed to too much of that rain. There are some minor vibrations from the mixing process, but not enough to be a big problem. You have only 3-phase, 230 volts, 60 hertz electrical power at your job site. A gasoline-powered engine produces this power. The motor must output 7.5 horsepower and must turn in steady state at 1,770 RPM. The required starting torque is 44 pound-foot, and the operational torque is half that at 22 pound-foot. Here's the motors that we can rule out from the start. We can't specify a single-phase AC motor because we don't have single-phase AC power at the job site. We don't want a 50 hertz 3-phase motor because the job site has 60 hertz 3-phase power. We can't use a wound motor 3-phase motor because we don't have the electrical interface for it. We can't use a NEMA Type E induction motor because our starting torque is 200% of operating torque, and starting torque of a Type E motor ranges only up to 190% of operating torque. You can buy a synchronous motor to run at 1800 RPM at 60 Hz line power. However, our motor needs to operate at 1770 RPM. The specs already specify a C-face motor mounting, so the other 3 types of mounting won't do. Here's a few items that are overspecified. We don't need a NEMA Type D motor, as that type of motor has starting torque up to 275% of operating torque. We only need 200%. NEMA Type A and B motors are not needed because there is no requirement for high energy efficiency. Cement mixers are not used 24/7. The TENV and TEFC enclosures are not needed because the motor will not be exposed to the rain. It is buried deep inside the concrete mixer. There is no requirement for an explosion-proof motor, so we don't need a TEFC-XP enclosure. The motor is located in a routine outdoor environment, so an IEEE 841-2001 severe duty motor would be overkill. Construction site is anything but a sterile environment. There's dust everywhere, so a washdown motor is certainly not needed. There isn't much left, only what we must have in our requirements. We need a 3-phase 230 volt induction motor, NEMA Type C. Power output is 7.5 horsepower and operational speed is 1770 RPM. It requires a starting torque of 44 pound-foot and operating torque of 22 pound-foot. We need a C-face mounting, and an open drip-proof enclosure is just fine. These motors are sold by a large number of vendors, so make sure to shop for a good price. This motor from Baldor has the specs we need, circled in red. There are plenty of other specs indicated, but none of them conflict with ours. The motor has 4 poles, but it doesn't matter how many poles it has, it does what we need. Here's the dimensions that you need to mount the motor to the internal frame of the cement mixer. The locked rotor torque is 46.3 pound-foot, about 5% more than the 44 pound-foot that we needed. That's okay. Operating torque is not specified, but we can calculate it from the operating horsepower, 7.5 horsepower, and the speed, 1770 RPM of the motor. Do the math and you will find that the operating torque is 22.2 pound-foot, slightly more than the 22 pound-foot that we need. Now let's study DC motors. Faraday's law of induction states that passing a current through a conductor in a magnetic field causes the conductor to move through the field. The force on the conductor is called the Lorentz force, F, equal to B times L times I, where B is the magnetic flux density, L is the length of the conductor, and I is the current. The direction of the force is per the right-hand rule, as shown in the diagram on this slide. Make an XYZ axes out of the thumb, index finger, and middle finger of your right hand. Point your right index finger towards the direction of current, and your thumb towards the direction of the magnetic flux from north to south. Your middle finger then points towards the direction of the force. Faraday also discovered that moving a conductor through a magnetic field causes current to flow in the conductor, creating a generator. E equals the generator EMF, also known as back EMF in a motor. And that's equal to B times L times V, where B is the magnetic flux density, L is the length of the conductor, and V equals the velocity of the conductor. The right-hand rule also determines the direction of the electric field and thus of the current. Now let's discuss how you apply torque to the rotor by running current through a coil winding bent into a loop. The 2 sides of the loop closest to the north and south poles of the magnet will have forces on them in the opposite direction. These forces create a torque on the coil. The torque T equals 2 times capital F times R. And recall that the force capital F equals B times L times I. So then the torque T equals 2 times B times L times I times R. The generator, or back EMF, equals B times L times V. But velocity V equals omega times R, where R is the angular velocity of the coil. So the back EMF equals B times L times omega times R. Passing current through the armature windings causes them to rotate through the magnetic field. Per Lenz's law, once the windings rotate, they become a generator, creating a current in the opposite direction to the applied current. The voltage produced in the opposite direction is the back EMF E sub B. The flow of current I sub A in the motor windings is then I sub A equals quantity E minus E sub B divided by capital R sub A. DC motors are found everywhere, which is not much different than AC motors. Large DC motors are used in electric autos, trains, elevators, and drives for rolling mills. Mid-sized DC motors are used in precision instruments, automated machinery, and robots. Small DC motors are used in appliances, tools, and toys. In an AC induction motor, current is conducted from an external line voltage only in the stator. The current in the rotor is induced from the rotating magnetic field of the stator. In a DC motor, however, current is conducted from external line voltage to both the stator and rotor. Moreover, the stator in a DC motor is often referred to as the field coil, while the rotor is called the armature. The armature coils consist of multiple windings of insulated wire wrapped around a soft iron core that concentrates the magnetic field. The ends of the armature wire winding are connected to a commutator, which allows each armature coil to be energized in sequence. The commutator touches a set of carbon brushes as it rotates, connecting the rotating coils to the external DC power supply. The carbon brushes touch a pair of slip rings in the commutator, one connected to each end of the rotating rotor coil. When the coil is powered, a magnetic field is generated around the armature. In the image on the slide, the right side of the armature is pushed down while the left side is pushed up. As the armature nears vertical, the net force on the wire that would keep the rotation going in the same direction approaches zero. As a result, the torque approaches zero too. The commutator then switches the DC supply to the other slip ring, reversing the direction of current through the coil. With current directions reversed, the forces continue to rotate the armature in the same direction per the right-hand rule. There are major differences between how speed is conducted in a DC motor versus an AC motor. Torque T in DC motors is proportional to I times B, where I is the current in the rotor coil and B is the magnetic flux between the rotor and the stator. In the simple DC coil discussed before, the proportionality constant was 2Lr, where L was the length of the coil and R the radius of the coil wire from the center of the motor. In a real DC motor, the proportionality constant is very complex, depending on the length and diameter of coil windings and the orientation around the armature. Speed in a DC motor, N sub DC, is proportional to V over B, where V is the voltage in the rotor coil and B is the magnetic flux between the rotor and stator. Speed in a DC motor is controlled by varying the voltage. There is no line frequency to worry about. You can decrease the magnetic flux to get more speed in a DC motor, but that would reduce the torque. In a DC motor, maximum torque always occurs at zero speed, either starting or stall, where the DC motor draws maximum current. Torque falls off as speed decreases, but not always linearly as shown in the graph. In an AC motor, torque was only maximum at zero speed for a NEMA type D motor. The other types of AC motors had a maximum torque called the breakdown torque occurring somewhere between 80 and 100% of full speed. The permanent magnet motor is a very specialized and expensive type of DC brushed motor. It uses permanent magnets for the stator instead of coil windings. This makes the stator magnetic field constant. The armature still uses brushes and a commutator. The constant magnetic field of the permanent magnet motor gives you linear torque speed curve and torque current curves. Energy efficiency is significantly higher than in a wound DC motor. Losses associated with the windings, such as eddy currents, don't happen with a permanent magnet. Permanent magnet motors are physically smaller than brush motors of the same power rating. As such, these types of motors are popular as power assists for auto windows and seats and for windshield wipers. They're also used in computer hard drives where space is at an ultra premium. We have a video demonstration of the teardown of a paper shredder. Inside that paper shredder is a permanent magnet motor, which we'll also tear down for you. The video is stored in YouTube. It also stars my cat Oliver, another reason to watch. The URL is given at the bottom of the slide. People invented the brushless DC motor for a simple reason. The carbon brushes, which conduct current to the commutator, wear out over time and need to be changed periodically. If the DC motor is in an inaccessible spot, changing brushes won't be fun. A brushless DC motor has no brushes, nor does it have a commutator. The armature consists of a series of permanent magnets. The stator still uses coil windings, and an electric commutator sequentially energizes the stator coils. This action generates a rotating electric field which provides torque to the armature. Hall effect sensors or rotary encoders sense the position of the armature. Sensor feedback determines when to switch the armature current. DC servo motors are brushless too. The motor has built-in sensors and electronics and firmware for a full motor control loop. The components shown in the photo on the right are packaged into one enclosure. DC servo motors are used to control position, velocity, or acceleration of the motor. Low inertial and high torque motors are used to give a fast speed of response. Here's a photo of a fully configured servo motor package. AC motors can be used as servo motors for very high loads and current surges. However, you will have a slower speed of response. Servo motors are popular in aircraft, machine tools, and precision instruments, where the need for precision control is paramount. They are effective in hobby projects because they're effective as teaching tools, and they are fun to program. Here's a standard block diagram of a motor control loop. Hopefully, it looks just like what you studied in your classes on control theory. Servo control circuitry is built inside the motor housing. Sensors include potentiometers, tachometers, and accelerometers. The control loop is generic for controlling motor position, velocity, and acceleration simultaneously. Recall that velocity is the first derivative of position and acceleration is the second derivative. This is evident from the two integral blocks on the right side of the loop. The desired position is sent through the PID control loop. The speed and acceleration of the motor is proportional to the difference between desired and actual position. Feedback compensates for errors in position and velocity. The desired servo motor cannot stop instantly when it reaches its desired position. A small amount of overshoot is built into the control system. Tuning parameters Kp, Ki, and Kd are used to fine-tune the overshoot curve for position. Kp sets the proportional term, Ki the integral term, and Kd the derivative terms in the PID control loop. These tuning parameters determine the solutions to the second-order damped natural frequency differential equation that governs the way that the motor approaches the set point. If you want fast speed of response, set the derivative term K sub d high, but that can give you a significant overshoot. If you want to make absolutely sure that you don't overshoot the set point, set the integral term Ki high. Be aware, however, that your response is likely to be very slow. Torque motors are toroidal-shaped and brushless. As the name implies, they provide very high starting torque, and they can continue to run successfully, even when the rotor is locked for significant periods of time. The high torque is accomplished by running high current to the stator windings, but this comes with a price. The large torque motors need cooling channels to circulate water around the windings in order to prevent overheating. Torque motors are essentially a linear motor rolled into a circle. There is no commutator, frame, brushes, or bearings. They can be used as actuators for direct drive mechanisms where large geared motors would normally be needed. Historically, they were used in tape drives because of their ability to maintain a tight tension on the tape far away from the spindles. A stepper motor is another example of a brushless DC motor. Unlike other motors, a stepper motor rotates at a fixed angle and then stops. The fixed angle is called a step, hence the name stepper motor. Think of a stepper motor as a quasi-digital device as compared to all other motors, which rotate continuously and through all angular positions. Common stepper motors rotate at angles as high as 90 degrees and as low as 0.75 degrees. The stator of a stepper motor has an even number of magnetic poles, each one with a coil winding. Each winding is connected to the one directly across from it, making up a stepper motor phase. Stator poles opposite from each other are magnetized in north-south pairs. High-resolution stepper motors have two rotors to optimize the resolution of the stepping. This design is called a hybrid stepper motor, featuring step angles as low as 0.75 degrees. The two rotors are made of permanent magnets, one polarized north and the other south. Numerous small teeth exist on the outer perimeter of each rotor, as well as on the inside perimeter of the stator. A stepper motor stays still when steady current is applied, unless you program the coil windings to make it move in an angular step. This is good news and bad news. It is good news if an external load tries to rotate the motor and you don't want the motor to move. Then the stepper motor will apply even more current to resist the load up until it reaches the holding torque. A load applied above the holding torque will force the motor shaft to rotate. The bad news is that the stepper motor is not very energy efficient. All other motors consume no power if they're not in motion. You don't need to worry about wasting energy if they're not in use. Stepper motors are used wherever precisely controlled angular motion is required, but there is no need for 100% analog resolution or constant velocity. They may be used in conjunction with a gearing system to give highly precise angular steps, also with high torque. Stepper motors can position a load without feedback, provided the load does not exceed the motor torque. This greatly reduces system costs and is a main driver of stepper use.